Okay, this is the September 2021 chemistry paper. It is also the November 2022 alternate paper, and this is question 6, the equilibrium question. It says steam, which is H2O in the gaseous state, gaseous water, reacts with hot carbon, carbon solid, at 1000 degrees according to the following balanced equation. 2 water plus carbon goes reversibly to 2 hydrogen plus carbon dioxide. Now this reaction, if you didn't know, is what is used as making hydrogen for the feedstock for the Haber process. So, but we're not doing that fertilizer thing anymore, but just out of interest, that's what they're doing. If you put coking coal and steam, you will produce hydrogen and carbon dioxide. Initially, 36 grams of steam and a certain amount of carbon were placed in a 2 cubic decimeter sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225 moles. Then it says to you, define the term dynamic equilibrium. This is a 2 or nothing answer. The stage in a chemical reaction where the rate of the forward reaction equals the rate of the reverse reaction. If this sentence does not have the word rate in it twice, it is completely wrong. We are referring to the rate of the forward reaction and the rate of the reverse reaction. Then it says calculate the equilibrium constant Kc for the reaction at 1000 degrees. So before we do any Kc calculation, we should practice writing our Kc expression. Okay, so the Kc expression is the concentration of the products, which are hydrogen, raised to the power of their coefficient. So what is my other one? Carbon dioxide, raised to the power 1, which I won't write, over, and this is where the big snag in this question is, the concentration of the reactants. So one of my reactants is water, and it is raised to the power 2. But you may not put in Kc anything that is a liquid or a solid. And this carbon right here is a solid. It does not belong in the Kc reaction. It is usually substituted in as 1. And if you multiply anything or divide anything by 1, you just basically don't have to show it. So this is the Kc expression, how it should be. Hydrogen squared, concentration of hydrogen squared, times the concentration of carbon dioxide squared over the concentration of water squared in the square brackets. Okay, so there's your Kc expression for 1 mark. Always make sure you write your Kc expression. Now we want to calculate the equilibrium constant, so I am going to use a rice table. Okay, but before I start, what other information do we have in the question? It says to you 36 grams of steam. So 36 grams of steam, I want to turn it into moles. So the number of moles of steam is going to be equal to the mass of the gas over the molar mass, which is 36 over 18. So initially I had 2 moles of steam. Okay, that's coming from the question. There is a 2 cubic decimeter container. So this 2 cubic decimeter container I'm going to use to find my concentration. It is going to be the number of moles divided by 2 in my rice table. And then here, this is where it's possibly going to confuse you. It says at equilibrium, it was found that the amount of carbon changed by 0.225 moles. Now the change is always the most important thing in any rice calculation, because the change is the only thing that is like kind of fixed by the mole ratio, because you can put any amount of reactants and products in a container, but the change will always be the same because of the law of conservation of matter. The atoms that change on the left must become the atoms on the right of the reaction. Okay, so you have to use this amount of carbon and the mole ratio. So if we start our table, it says ratio, and now the carbon we don't actually need, but we can put it in the table so long as we don't do any calculations with our final Kc here. So we've got water, we've got carbon, we've got hydrogen, and we've got carbon dioxide. That is the first thing on our table. Now I always like to make it very clear which ones are the reactants and which ones are the products. Okay, so we should make sure that we've got a good dividing line between the reactants and the products, because why? These will decrease and these will increase. So when we get to the change, we have to be paying close attention. So now when you draw these tables, do not be lazy and just write rice down the side. You actually have to write exactly what you're doing. So my initial moles, we know that the carbon doesn't really matter, so I'm leaving the carbon blank, okay, because it says it's a certain amount. But we do know from that other calculation, the 36 grams of steam translates into 2 moles of water, and we had no hydrogen and no carbon dioxide. Then we come to the most important thing, the change, which is also in moles. We have to write this out, okay? They told us in the question the amount of carbon changed by 0,225 moles, okay? And so we have to use this and the mole ratio to calculate everything else. We are not going to use the carbon because it's a solid in the Kc, but due to the law of conservation of mass, we can figure out that over here it is going to be 0,225 times 2, which comes out to 0,45. This is going to be a decrease. And then how did I get the times 2? It's from my little mole ratio here. Can you see 1 mole to 2 moles, 1 mole to 2 moles? So this one is also going to be 2 times 0,225, which is 0,45, but this is going to be an increase. And here we've got a ratio of 1:1. So this one's going to be 0,225, the same as the carbon. And now we don't need to worry about the carbon anymore because the carbon has got nothing whatsoever to do with our Kc calculation. Okay, we just used it to figure out the change in moles. Now we need to find the equilibrium moles. Okay, and this is 2 minus 0,45. because we are decreasing from what we had initially. So this gives me 1,55 moles. This was 0 plus 0,45 because it's a product, it's increasing. This gives me 0,45. And this one is 0 plus 0,225, which gives me 0,225. So now we've found the moles, but Kc asks you for the concentration at equilibrium. Okay, so to do this, we want an answer in moles per cubic decimeter. So you can use C equals N over V if you like, which means we are going to divide by 2 because the container is 2 cubic decimeters. So it's 1,55 divided by 2, which is 0,775. 0,45 divided by 2, the volume of the container gives you 0,225, and 0,225 divided by 2 is 0,1125. Please do not round these numbers off. Please keep these numbers as accurate as possible until the last step. So now we've got the equilibrium concentration. We can now go and work out the Kc value. So we go to our table. What was our concentration of hydrogen? 0,225, which we must raise to the power of 2. What was the concentration of carbon dioxide? 0,1125, which is to the power of 1, so we don't write the power. And the water was 0,775, which we must raised to the power 2 because that is a coefficient from the balanced equation. So if you plug that all in your calculator and you have done everything correctly, you will end up at 9,48 times 10 to the negative 3, which is not needing a unit because Kc has no units. And so this is the Kc value for this reaction. So I'm about to move on with the question, so I'm going to erase all of this ink. Pause the video if you want to be copying the calculation, but for now I am going to erase all of the ink. Okay, so now let's look in the second half of this question. It says to you, the graph shows how the rates of forward and reverse reactions change with time. Give a reason why the rate of the forward reaction decreases between T0 and T1. So here's T0 and T1, And if we look at the key, the forward reaction is the solid line. Okay, so we should always pay attention to the key in case one day they try to trick you by making the forward reaction dotted. So it says to you, why is the rate of the forward reaction decreasing? Look here, it was very high, okay, and then it went lower over here. What is happening is the steam, which is a reactant, okay, is being used up. And so if the steam, which is a reactant, is used up, it means its concentration drops, okay, and if the concentration drops, rate of reaction decreases. So that is why it is decreasing. So the main reason is a reactant is being used up. Then it says, what change was made to the equilibrium mixture at T3? So if we have a look over here, here is T3 over here, and if we follow the line up, we can see both the forward reaction and the backward reaction increased. And what is unusual is that they increased exactly the same amount. So when we do equilibrium graphs like this, we have to start thinking about what affects reaction rate. So what things can cause reaction rate to increase? Things that cause reaction rate to increase is an increase in concentration. Okay, but remember, equilibrium theory is governed by or guided by reaction rate theory. So we can increase the concentration, we can increase the temperature, or we can add a catalyst. Okay, and of these things, in a reversible reaction, the only thing that increases the rate of the forward reaction and the rate of the backward reaction equally is addition of a catalyst. So what change happened at T3? They added a positive catalyst. Okay, that is the only thing that will make both reaction rates increase. Now it says to you at time equals T2. At time equals T2, let's have a look on the graph here. Time equals T2. The temperature of the system increased. So can you see here? Look at this one curve. It has gone up steeply. Okay, and look at the other curve, it has not gone up so steeply. So the forward reaction increased more. Yes, the backward reaction increased less. Both reaction rates increased, so that makes sense. If we increase the temperature of a system, it will increase reaction rate. But now, is the forward reaction exothermic or endothermic? If the rate of the forward reaction increased more, then we can say that the forward reaction was favored. Okay, so if an increase in temperature, okay, increase in temperature, I'm answering 6.3.4 before 6.3.3 because I have to do the logic before I guess the answer. So an increase in temperature favored the forward reaction. Okay, you can see that the forward reaction went up much more than the backward reaction, but according to Le Chatelier, an increase in temperature favors an endothermic reaction, because Le Chatelier says that if you make a change in the system is going to try and reverse that change. Okay, so the increase in temperature favors an endothermic reaction, and the forward reaction is favored. Therefore, the forward reaction must be endothermic, because increase in temperature favors an endothermic reaction, and of the two reactions, the forward reaction was favored more than the backward reaction. And that is the end of this question.